A good day to everyone. I'm Kshirin Shetty and I will be presenting our paper on robotic suturing, an attention-augmented deep learning approach using demonstrations co-authored with Monisha Sharma under the guidance of Dr. Rashmi U. Robotic suturing and deep LFT. Robotic assisted surgical systems, most notably the Da Vinci surgical system, have redefined modern minimally invasive surgery. They provide surgeons with enhanced dexterity, tremor reduction, and high quality visualization. These features have collectively enabled surgeons to perform delicate and complex procedures with smaller incisions, less blood loss, shorter recovery times, and reduced risk of complications compared to traditional open surgery. Among surgical subtasks, suturing is widely recognized as one of the most technically demanding. It requires precise needle placement and bimanual coordination, where small errors in suturing can cause leakage, wound reopening, or tissue damage, directly impacting patient safety. Suturing, in particular, is one of the most challenging and error prone surgical tasks, making it a prime candidate for automation. This is where artificial intelligence, and especially deep learning, can make a real impact. What are the limitations of current solutions? 1. Heavy visual backbones. Most prior methods use networks like VGG19 or ResNet 152 for feature extraction. While powerful, these are too computationally heavy for real time deployment, causing latency, high memory use, and making them impractical for surgical robots with limited onboard hardware. Second point, weak temporal reasoning. Suturing requires modeling long sequential actions where each step depends on the previous needle placement and tissue states. However, existing systems rely on shallow LSTMs or GRUs, which capture only short term dependency. This leads to errors such as misaligned stitches or skipped steps, since surgical intent unfolds across longer horizons. Third point, simplistic multimodal fusion. Vision and kinematics are usually combined through late fusion, concatenating features at the end. This misses critical interactions like how tool trajectories affect tissue deformation or how visual cues guide motion. Now, as a result, cross modal synergies are underutilized, limiting accuracy and generalization. Noting these limitations, we aim to design a model that overcomes these gaps by being efficient, temporally attentive, and deeply fused. Our model starts as visible through the approach in the workflow demonstrated. It starts by taking surgical video frames and passing them through a compact, efficient net B not backbone, which we call efficient suture net, to extract per frame visual features. At the same time, the robot's kinematic signals, that is, joint angles and effector positions and velocities, are encoded into a compact representation. These two modalities are combined early using feature wise fusion, allowing the model to capture interactions between tool motion and tissue state. The fused features are then fed into a multi layer LSTM, which captures sequential dynamics over time. On top of that, a multi head self attention module highlights the most critical temporal moments in the sequence. Now, finally, the processed representation is decoded through two heads, where one predicts discrete surgical actions and the other predicts continuous tool trajectories, producing the outputs needed for autonomous suturing. The difference is brought about by our approach as compared to the limitations which were posed are four things: efficient net B not visual encoder, early multimodal fusion, LSTM with multi head self attention, and a dual headed output. Now let's get into each of our unique architectures. Step 1, which is your visual encoder. The visual encoder is a critical part of our architecture. We use efficient net B naught because it provides an excellent trade off between accuracy and efficiency using a far fewer parameters than large networks like ResNet 152, while still capturing rich feature representation. Its compound scaling balances depth, width, and resolution for optimal performance. We employed depth-wise separable convolutions, which maintains expressiveness at a lower cost. The early layers are frozen to preserve general low-level features, while the deeper layers are fine-tuned specifically for surgical images. The encoder outputs semantic embeddings representing tool tissue interactions and scene context, which are then fused with kinematic data to form the foundation for precise real time action and trajectory predictions. The second step involves modeling temporal dependencies. Now, to model the sequential nature of suturing, we use a three-layer LSTM to capture the order and dependencies across surgical steps. For example, moving from needle insertion to pulling and release. While the LSTM encodes temporal context, it can sometimes dilute focus over long sequences. To address this, we add a multi-head self-attention module on top of the LSTM. This attention mechanism identifies and emphasizes critical moments in the sequence, such as tool tissue contact transitions or complex curved motions, while downplaying redundant frames. By combining LSTM and attention, the model effectively learns both the overall temporal structure and the clinically important keyframes required for precise suturing. The next important part of our approach includes the action and trajectory prediction. Our framework concludes with two decoding heads: the classification head, which predicts the current surgical action, such as needle insertion, pulling, or release, providing interpretable insight into the model's decision. Now, the second head, which is your regression head, predicts fine grained 3D Cartesian displacement vectors for the robotic tool, ensuring precise motion control. This dual task setup captures both what to do and how to do it, aligning predictions with real surgical workflow. During training, we balance the losses with weights of zero point 0.7 for regression and zero point 0.3 for classification, prioritizing precise motion over action labels. This network is optimized using AdamW with cosine and near learning rates, and we employ data augmentation, gradient clipping, and early stopping to improve stability and generalization. This diagram represents the workflow of the entire architecture which we have come up with. So, this process starts with a raw data set which contains various types of data related to a suturing task. This includes kinematics, poses, 6 camera videos, and targets. This raw data is then split into and fed into two separate processing pipelines. The first one being your image pipeline. This pipeline processes the video data. It extracts frame, resizes it, packs it for efficient processing, and filters it into training and testing set. And the second pipeline, which is your robot state pipeline, handles the non visual data like kinematics and poses. It downsamples CSV files and aligns them with the image from the other pipeline. This is to make sure that the visual and state data correspond in time. This processed data from both image and robot state pipeline is then fed into your deep LFD suturing framework. This framework is a deep learning model built with several components explained, where we include your efficient net, LSTM, and your fusion and attention. The CNN that extracts features from the image data, LSTM, which is suited for processing sequential data, and your fusion plus attention, where it fuses the feature from CNN, and your attention mechanism helps the model focus on the most relevant parts of the data. The output of this framework is two distinct predictions: your predicted actions and your predicted trajectories. Your predicted actions are your suturing step classes, which represent discrete actions the robot should take. And the predicted trajectories are the 3D end effector paths, which represent continuous precise movement the robot's end effector should follow to complete the suturing task. Now let's look at the results. We evaluated our model against strong baselines including VGG19, ResNet 152, AlexNet, customized CNNs, and RNNs. Our proposed architecture achieved the lowest mean absolute error of 0.025, representing roughly a 40% reduction compared to VGG19. It also achieved the lowest root mean square error and maintained a very high squared R value. For action classification, our model reached over 99.8% accuracy within a zero point 0.1 tolerance, demonstrating precise step prediction. Importantly, this high performance is paired with efficiency. Our model has only 15.7 million parameters and a size under 60 MB compared to ResNet's 152 61 million parameters. It runs at 0.175 seconds per frame, approaching real time inference and making it feasible for surgical deployment. Finally, the model is interpretable. GradCam visualizations highlight tool tissue interactions, while temporal attention emphasizes critical transitions such as needle insertion and release. These results show that our architecture set a new standard in accuracy, efficiency, and interpretability for autonomous suturing. This slide emphasizes on the performance analysis of RCNN. As visualized, we have compiled the primary test metrics, accuracy at different threshold, error distribution percentile, model complexity, performance versus inference time, advanced performance metrics, efficiency metrics, normalized error metrics, and an overfitting analysis. Beyond numbers, we also conducted qualitative evaluation. The attention mechanism was observed to focus on frames where tools interacted with tissue or where motion transitions were particularly complex. This suggests that the model is learning to prioritize clinically relevant moments. In trajectory regression, our predicted tool paths closely follow the ground truth expert demonstration, showing both smoothness and accuracy. These qualitative findings reinforce the quantitative results and highlight the interpretability of our approach. We have also implemented a tension heat map, which shows that the model focuses on key temporal transitions in the suturing sequence. For our experiments, we focused on autonomous robotic suturing using the deep LFT benchmark dataset, working entirely within a fully simulated environment. The entire framework was implemented and tested on standard laptops without any reliance on physical robotic hardware, allowing us to efficiently develop, train, and validate the model in a controlled setting. The future work or the future scope, which we had to say, was one, simulation only validation. Model performance has been evaluated in simulated environments for control testing. Second, optimized for single tool suturing where multi instrument coordination is not yet addressed. Integration with real robotic system remains a future step, and this is currently specialized for suturing, where generalization to other surgical procedures is planned for future work. Thank you.